So now let's move on to the idea of estimating the delay of these gates, right? I want to ultimately use this gate to either again charge a capacitance or discharge a capacitance, like I've told you many times. That's the only purpose of this course. How fast can I charge? How fast can I discharge? So we have to estimate these delays, given that we have now had different kinds of sizing that is happening there, right? So for that, first we have to estimate the capacitance on these arbitrary gates. Okay, so let's look at the capacitance. Let's start with our inverter. Maybe I should draw this bigger because I need to put a lot of caps there. Okay, let me also draw the body node. This is connected to VDD. This is connected to ground. Now, what are the capacitances for this inverter? Yeah? Yeah. So basically from gate to source, there is one capacitance. Right? This is the CGSN. Then from gate to drain, there's one more capacitance, CGDN. Right? Then there is one capacitance like this, CDBN. Right? CSBN. Right? And then there is also a CGBN. Okay. Similarly, I have capacitances on my PMOS transistor as well. Same number of capacitances. Okay. The only difference is because this is size 1 and this is size 2, the capacitance now will become twice. Remember, all the capacitances that we derived scale linearly with W. That was our primary conclusion from that module, right? So let me put that down explicitly. All caps scale as proportional to W. Therefore, you will have, if the unit capacitance for a PMOS transistor, that is a PMOS transistor with width 1, is CGSP, then this will be 2CGSP, right? And actually there is nothing to choose between these two, between the NMOS and PMOS. So all, if the CGS is CGS for the NMOS, then if the same width I use for the PMOS, then that is also CGS. There's no big difference there, if you remember. Just because there are holes there, the capacitances don't change, right? So let me just write that down. This is 2CGDP, right? Then I have this CGDBP and CSBP twice. All this will be twice. And yeah, correct. You're right. I'm just saying, I've just called it CGSP. I will now say CGSN equals CGSP. Right? I'm just marking it differently. So the first thing to do is, these capacitances, there are too many capacitances here, right? So for our first order back of the envelope calculations, we don't need these many capacitances there. In the sense, I am not worried if the value of CGD and CDB are slightly different. The fact is both of them scale linearly with W. Okay, so first assumption I am going to make is assumption 1. I will lump all caps. Okay, first what I mean is this CGD, right? I'm simply going to make it a single gate capacitance. Ideally, you have to break it up as a Miller capacitance, part here, part there and all that. You can add all of them. I'm saying break everything and simply get a capacitance like this on the NMOS transistor. Similarly, for the PMOS transistor, I'm going to get one capacitance. I'll put the values there now, right? The CSB is useless because it's connected between ground and ground. So I can neglect that capacitance. Similarly, I can neglect this capacitance, right? Now the CSBP is going to VDD, but that's like an AC ground, right? So therefore, I am going to bring all the capacitances to ground, all caps to AC ground. So what happens is my NMOS transistor now has one capacitance. Similarly, the PMOS transistor has another capacitance. Now we are going to make the biggest assumption which will make you question why we did all those calculations in module 1. We are going to assume that the CGD and CDB are basically of equal magnitude. You go back and look at the calculations that you did, the capacitances are not off by lot. Okay, so third assumption is all caps are equal. Which implies this is C, this is also C. Of course, this is size 1, this is size 2. Therefore, this is 2C and this is 2C. Okay, go back and check your calculations. The drain to body capacitance would not be very different from the gate capacitance, net gate capacitance that we got, right? And the primary point is, since all of them scale with W, my error is not cascading. It's not like I have a larger error if I do larger W, right? They all scale well and it's reasonably accurate there. Okay, in reality, of course, if you run it in a simulator, you will get a slight difference, but that's not for us to worry in this the theory part, because the inferences we are going to make from this calculations that we are going to do will still be consistent with the assumptions that we are making here. Okay, so net thing I can do is take an inverter and simply write it as a sum of two capacitances. This is 3, now wait, I got to put a capacitance, 3C, and this is also 3C, where C is basically the gate capacitance of a unit transistor, NMOS transistor. This is C, net gate capacitance of a unit NMOS transistor. That's what this C is. Okay, and of course it's also equal to drain capacitance by this assumption. Clear? Okay, now I want to take this understanding and identify what the capacitances are for a NAND 2 gate. Okay, so let us look at this. right? So what do I have? At the gate of each transistor, I'll have a capacitance. At the drain of each transistor, I'm going to have a capacitance, right? And maybe at the source also, depending on whether the source is grounded or not, I will have to put a capacitance there as well. So let us now go ahead and mark these capacitances. I have a cap here, right? I have a cap here. Then I have a cap between the drain and ground for the PMOS. I have a cap between this drain and ground for this PMOS. So sizes, by the way, are 2, 2, 2, right? So what are the capacitances now in terms of C? All of them are 2C. So this is 2C, 2C, 2C and 2C. Okay, I will now draw this NMOS stack separately so that it becomes clear. Output Y, this is 2, 2. So what's my gate capacitance? Yeah, 2C. What's this capacitance? 2C, right? Now I'm going to put one gate capacitance, drain capacitance here, 2C, right? The source of, let me call it N1, N2, right? This is the sizes. The source of N2 is going to have a capacitance of, yeah, 2C again, right? Wherever you have a node, you got to put a capacitance and scale it by the width. The drain of N1 will have a capacitance of 2C. So what is the net capacitance here? Yeah? No, not, forget the PMOS. I'm talking only of the NMOS. 2C, right? What is the net capacitance here? 4C, okay? And I have 2C, 2C, okay? Now here is a slight trick that we will use from the layout, wherein this intermediate capacitance is not going to be 4C. It will actually be only 2C. Okay, I'll tell you why. And this will also help you do the layout for your NAND gate, that is your part of the assignment. Okay, I was asked not to use this green, right? Green is not visible from behind. Is it? Magenta is not. Okay, I will use blue. Okay, what about this green? Yeah? Is this visible? Okay. Good. So let me just, okay. So what I'm going to do is I'm going to now go to the layout of these two, of this NAND gate. Okay. So I have a width of 2W here and I have two gates. Right, these are my two NMOS transistors which are in series. So this will basically be my, maybe I should just put a metal one here, ground, and I will connect this to ground. Okay, there are appropriate contacts and all that. So this is basically nothing but my series stack from the output Y to ground. So these are my inputs A and B. So the gates are going to be connected to inputs A and B. A, B. Similarly, I have a PMOS this thing, but now this PMOS is going to be in parallel, right? So, sorry, I got to, yeah. So what do? I'm going to simply extend this gate all the way. And if you remember, it is not possible to bring these two transistors PMOS and NMOS very close because there is a well spacing problem, right? Remember, this PMOS is actually sitting in a N well and the NMOS is sitting in a P well, right? This is my N well. So now I have my VDD line which is sitting here, VDD. So now what am I going to do? I am going to construct this parallel PMOS stack. Right, and take it up to VDD, right? So what do? I'm going to simply connect this guy to VDD, this guy to VDD. This intermediate node that is there is going to become my output node Y. This diffusion is actually this particular diffusion here, right? This thing is actually my output Y and this is my output Y, right? If this is node X, then this is my node X, right? So then I have to do something else. I have to basically now draw metals and short my output like this. Okay, this is how you have to do the layout for your assignment also on similar lines. Clear? So now we will look at the capacitance terms that are coming, right? If I had this guy as two separate transistors, what would I have done? I would have basically made it one NMOS transistor, another NMOS transistor, right? Then I will put a gate here and I would have put two metals. Sorry, I would have connected it to a metal, M1. This is what I would have done if I wanted to keep these as two separate transistors. But now these transistors share a diffusion. Diffusion is basically my N plus, right? They share that diffusion and also there is no contact on that. What do I mean by contact? It means that this node X is not available to the outside world. You can access Y, you can access A and B. You cannot access X from outside, which means there is no contact that is made, and therefore I don't need to give any minimum spacing between these two diffusions. I can pull the transistors very, very, very close, right? Therefore, this distance, I can simply remove this whole metal thing, right? And move the transistor as close as I can to it and draw my gate. Okay, remember that when we spoke about the thing, let me just undo this so that you can use the previous. Remember that when we derived the capacitance of the drain and source, we were actually looking at this cross-sectional area. And that's why we got a C, we got a capacitance of C from here, a capacitance of C from here. And if it's, of course, W is higher, then it is 2 into C. And therefore, we said it has to be 4C in that diagram. But now if I bring these two diffusions so close, it's effectively like just one diffusion. You get it? That's the idea that we are using. So if you look at the picture of the transistor itself, it would be something like this. N plus, my gate. This N plus will be shared. So my other N plus will come here and this will be my gate. So instead of having 4 N plus diffusions for 2 transistors, I will have only 3 diffusions for 2 transistors. The reason is, it's not just that it is shared, the diffusion is also uncontacted. For example, I can ask you, even the PMOS, the diffusion is shared, right? If you look at this thing, The diffusion is shorted. The diffusion is shorted here. The difference is I need to put a metal contact here. Because I need to put a metal contact, I need spacing. And therefore, I have to keep the transistors far apart. And therefore, the capacitance is like each transistor will contribute to its capacitance. So the golden rule is if it is an uncontacted shared diffusion, then you don't double count the capacitance, right? So here this is an contacted shared diffusion, and therefore implies do not double count cap. Therefore, I will redraw my NAND gate with the net capacitances as follows. Inputs are shorted. I have one capacitance between A and ground, other capacitance between B and ground. How much is the net capacitance on A and B gate? On each input, what's the total capacitance? Yeah? 4C, right? Each transistor gave me 2C because the widths are 2 each. Net capacitance is 4C. 4C. Okay? On this output node, what's my total capacitance? PMOS plus NMOS. 6C, right? Because it's 2C from each PMOS transistor, because it's a shared diffusion but a contacted diffusion, and therefore it is 2C from each PMOS transistor and 2C from the top NMOS transistor. So this is 6C. And what's the intermediate capacitance? It is 2C. Okay, any questions here? This, if you don't look at the layout and the physical picture, you will not get this idea of uncontacted, contacted shared diffusion. Okay, but luckily you're going to do it in your assignment now. You'll see it for yourself. You can try it and see, right? You just see for the PMOS transistor how much space you need. You have to keep it far apart. Therefore, the diffusion will be large. It will be like 2 diffusions. NMOS, you can bring it really close without any DRC violation. That's the idea, right? Any questions here? No. Where? Ah. Oh, yeah. See, for the inverter, the bottom transistor source was shorted to the body. Both are connected to ground. See, the reason is, if you look at this NMOS transistor stack here, this guy's body is grounded. This guy's body is grounded, but the source is not. Therefore, I have to bring in that capacitance there. Only because in an inverter, source and body were grounded, I could remove that capacitance out of the picture. There is a capacitance, yeah, so that's what I told you. So that becomes like a capacitance between the input and output. Now that you do Miller capacitance and split it as you know this thing. So I'm saying you lump all of them. Effectively, it's like 1C here, and the drain also has the same C. Correct. Yeah. Any other questions? Yeah. Yeah. you can bring it as close as you can. Effectively, it will be like one diffusion. That's all. You see, you try it in the layout and see, you'll know. Okay. So then we'll stop here. We'll continue on Monday. Thank you.